Welcome to this NPTEL course on Advanced Reinforced Concrete Design. So far we have completed four modules. We are getting into this fifth module on understanding the behavior and design for flexural loads. Okay, so this module we will do it for next 2 weeks. In this first the module, I think we have divided them into five parts, five modules. The first one, we are going to talk about the background to the flexural theory and how we can do moment curvature analysis. In the module 2, for the fifth module, or part 2 of the module 5, we are going to discuss about the effect of concrete strength and reinforcement ratios. And so, what is the meaning of reinforcement ratio? If I start putting more amount of steel or less amount of steel in the concrete section, so how the moment curvature analysis is going to change. So that is what we're going to look at it in this part 2 of this module. And part 3, which is module 5.3, we are going to discuss about what is the effect of axial compression. Sometimes beams also can have some level of axial compression, and what is the effect of that. And also, if I start putting some compression steel, which is doubly reinforced section, how that moment curvature analysis is going to change, that we're going to look at it in module 5.3. And in the fourth part of the module, we're going to talk about flexural design aspects using IS code provisions, that is IS 456. Okay, and in the fifth part again, we will continue and we will solve some examples using IS code provisions. So one thing that I would like to note is in the first three parts of this module, we are going to get the use the actual constitutive relationship, okay, with some assumptions. For example, in the material aspects, we talked about the parabolic stress strain curve model, and similarly, we also used the elastic perfectly plastic model for steel. So that is the constitutive equation that we are going to use for the first three parts. In the next two parts, that is part 5.4 or module 5.4 and module 5.5, we are going to use the design stress strain curve that is specified by the IS code. Okay. So as we have discussed in the material chapter, the IS code provisions, they use the design stress strain curves which are factored. They use less strength, and the constitutive equations are different than what we get when you test concrete cylinders or sustain curves. Okay, just to ensure that we predict the strength, other parameters in a conservative way. The code is using design stress state curve. So, so the first three parts of the module, we are going to understand the behavior. Once we understand the behavior, the design process will become very simple. So, the part 4 and part 5, we are going to use the design stress strain curves and see how the IS code provisions can be used to calculate the capacities. Right. So let's get into the part 1 of this module 5. We're going to talk about background to the flexural theory and how we can do the moment curvature analysis. Okay. Right. So what are the expected learning outcomes from this part? The student, after attending this module, he or she should be able to explain the behavior of RC member under flexure and should be able to understand and explain what is elastic beam theory, how the basic relationship for bending theory was derived, and we are also going to use equivalent stress block parameters for calculating the moment curvature behavior. So we will explain how these equivalent stress block parameters are derived, and also we will one should be able to explain how the moment curvature analysis is done. Okay, and finally we will also discuss what are the different types of failures that are observed in flexure. Flexure is nothing but bending. Okay, so it's a nomenclature that we use when we say beam is undergoing bending or flexure. It is basically under bending mode. Right. So let's look at this example here. So what we are seeing here is a beam that is subjected to some uniformly distributed load, like the one that we are seeing here, right? So it is subjected to some load which is W per unit length. In addition to that, you also have this point load, which is P, right? And one thing to note down here is here the N represents the axial load. In this case, I have taken the axial force to be 0. So this is some kind of a generic loading that the beam is subjected to. So now, if you look at, from your structural analysis course, this is a statically determinate beam. Using equations of equilibrium, you should be able to get the bending moment diagram and shear force diagram. So you're going to get this kind of a variation that is drawn here, right? This is your bending moment diagram. If I take it at a particular section, you can see that this is the bending moment that you're going to have. So this is the bending moment. Bending moment is an internal force, okay? And the effect of external loads, which is your uniformly distributed load or point load, it gets manifested in the form of internal forces at every cross section, and that is what we are actually using it to design the reinforced concrete members, right? So if you look at again, draw the free body diagram from your basic engineering mechanics course. So you can draw once you cut a section, and if you look at the left side part of the beam and right side part of the beam, and then you are to keep the two parts in equilibrium, you need to have some internal forces. So those are the internal forces that we are going to use it for designing your reinforced concrete section. So for example, you see here the shear force and bending moment you expose once you cut, right? So these are internal forces. So this is what we are going to use them for design. So you know that from your structural analysis. Now, so again, the moment can be expressed, or the resistance comes from a couple where concrete gives compression force. Concrete is weak in tension. You see that we put some steel that is going to give some resistance for the tension. So C should be equal to T to satisfy the force equilibrium, horizontal force equilibrium, right? Then they form a couple to provide resistance to this internal force of bending moment, right? So this is the way it is there. So for me to design the reinforced concrete beam, first I need to do structural analysis and find out the distribution of my bending moment diagram. Then at each cross section, I know what is the bending moment that is acting on this section. Then accordingly, I can design either as a singly reinforced section where we put steel only on the tension side, or as a doubly reinforced section if the bending moment is high, then we start putting steel both on the tension side as well as on the compression side, right? So so let's see the basic behavior for bending. We know that elastic bending theory or Euler bending theory, right? When a bending moment is applied to the straight prismatic beam, we know that if I have this beam, let's say in an undeformed shape, and if I mark some grid lines, horizontal and vertical lines, okay, let's say for this is a simply supported beam, is subjected to a simple point load on the midspan location. So this beam, from statics, we can find out the bending moment diagram. Now this is before any, let's say the load is 0 at this point of time. So this is how the undeformed shape is going to look like. Or otherwise, the grids are going to remain exactly where they are. So the horizontal lines, vertical lines going to remain horizontal and vertical. The moment I start increasing this load P, then what happens? The beam is going to bend because it is subjected to now a bending moment, and the bending moment is varying linearly, that we know how to calculate this bending. So you can see here that now this vertical lines has rotated and the horizontal lines have become curved. Okay, so this vertical transverse lines, though they remain straight, but they have undergone some rotation. However, the longitudinal or horizontal lines, you can see that they have become curved. Okay, so this is the way in bending the beam is going to deform, and this is in a three-dimensional uh, illustration. So you can see that after deformation, the vertical lines are going to remain straight. However, they're going to rotate, and horizontal lines become curved. So if you look at it at the top, you can see that it is the elemental length is getting reduced, and at the bottom it is getting, so horizontal line is getting extended. So the bottom is going to have tension and the top is going to have compression. So we know this. Correct. So then also to define, there is a location. If you look at it in a three-dimensional fashion, there is going to be a surface along the longitudinal length of the beam. That is basically the fibers will not undergo any change in length, or they are not going to undergo any deformation. That surface is what we call it as a neutral surface, where there is no change in length. Okay, but if you look at a cross section, then the surface will become a line. So that is what we call that as a neutral axis. In this case, because the illustration is given in a three-dimensional fashion, so there's going to be a surface in which the deformation is not going to be there, or there's not going to be change in length. Right. So what are the assumptions that we have made in your elastic beam theory? Okay. So as we've said, the straight line remains straight, however, they undergo rotation. Okay. So that indicates that the sections, every cross section you see that it is going to, before deformation it was straight, and after deformation also it is going to straight, it is going to be straight, however, it is going to rotate. So the plane sections normal to the beam axis remain plane after bending. That means an initially straight beam where the strain is varying linearly over the depth of the section. As we have seen in the previous slide, the top fibers were getting shortened, the bottom fibers were getting elongated, and you can see that there is a rotation of this vertical line, and also the fibers are getting either elongated or compressed, depending upon whether you're looking at the top fiber or the bottom fiber. That tells that strain is varying linearly over the depth of the section. Now, for a reinforced concrete member, we have seen it in your material constitutive relationship. How is the stress strain curve behavior of concrete? Let's say if you're taking strength of concrete less than 40 megapascal, we have seen that the stress strain curve behavior of concrete is going to be basically parabolic. So let's say this is FC, this is epsilon C. So we have seen that this is going to be parabolic relationship, right? And this all the notations you know. So this the peak stress is called as compressive strength of concrete, cylinder compressive strength, which is denoted as F prime C, and the strain corresponding to this peak stress is epsilon prime C. Usually we take that as 0.002, right? For strength up to 40 megapascal, concrete reaches its peak strength at a strain of about 0.002. So it is going to 6. So, but which one do I call that as the ultimate strain at which we define that concrete is going to fail in compression? Usually we take this value as point, this value which is epsilon Cu. Okay, so epsilon Cu is usually taken as 0.0035. Okay, so it's an acceptable value. So if you look at a AC code, it takes 0.003, but IS code specifies that you can take it as 0.0035. In fact, people have done in the past some experiments, and they found that it is this ultimate strain is also function of the shape of the cross section. But usually we deal with rectangular cross sections or T beams, either. So for that, 0.003 or 0.0035 is good enough. So this I have to define this failure strain. So we define this failure strain in compression as 0.0035. Right. So now that we have seen this, let me erase this. Okay, so for the part one, to understand the behavior, okay, so what we are going to take is use this parabolic model that we have set, which is a hog-nested stress strain curve that will be used. And for the part two, when we are doing calculations as per your IS code 456, then we are going to use the design stress strain curves that are specified by the code. Okay, so that is what we are going to use. Okay, so for the part one, we are going to use the constitutive equation that what we are going to observe when you test a concrete cylinder, for example, in compression, we'll get this parabolic model for strength less than 40 megapascal. It's a good enough. It's a reasonably good assumption. That's how the shape will be. But if you test high strength concrete, of course, the shape is going to change. That we have discussed. We have to use Thorenfeld's model. Okay. There are lots of other models are also available, but for less than 40 megapascal, usually parabolic model is used, and for more than 40 megapascal, you can use Thorenfeld's model. So that is what we are going to use. Similarly, for steel, we are going to elastic, perfectly plastic model, what we have used in your axial behavior also, to illustrate what is the effect of different parameters. However, when we go and use IS code, your stress strain curves will be the design stress strain curves that are specified by the IS code. Now, depending upon what kind of code that you're using, for example, if you're using IRC code, then the constitutive equations will be different that we discussed in the material chapter. So, don't worry about why you have to use different constitutive equations. Tomorrow, let's say if you have to use a special concrete like ultra high performance concrete or a steel fiber reinforced concrete, then whatever the stress strain curve that are specified by the IS codes are not actually valid. So you have to test and develop your own stress strain curve and use it for estimating the capacities and design the sections. So the idea for this part one is to, if you are given a set of constitutive equations, how to use them to understand the behavior. Then part two, that is in the fourth and fifth parts of this module, we are going to discuss how to do the calculations using the design stress strain curves that are specified by the IS code. So please do not confuse between these two. Okay, so usually we ignore the tensile strength of concrete because the tensile strength of concrete is very low, and we have seen that even in the axial behavior, at a strain of about 0.00011 or so, the concrete cracks in tension. So it's a very low strain, and the strength is also roughly 10% of your compressive strength is what we assumed in your last point. So it's not going to really make a big difference. So that's why what we do is usually we ignore the tensile strength of concrete. However, if you're using a special concrete like ultra high performance concrete where you put 2% of steel fibers usually, or a steel fiber reinforced concrete where you put a lot of steel fibers, then this assumption will not be valid. Okay, for a typical normal concrete with or not reinforced with any fibers, ignoring the tensile strength of concrete for ultimate capacities is a good conservative assumption. Okay. So as we've said, for steel also, for part one, we are going to use elastic plastic model. For design, for part two, using the IS code provisions, we are going to use a design stress strain curves that are specified by the IS code. Okay, where we'll also use partial safety factors. For steel, you know that partial safety factor is 1.15. For concrete, it is 1.5. So we will reduce the actual stress strain curves by a factor, or the characteristic curve by partial safety factor, to get your design stress strain curves, right? So when we do the design calculations, again, we have to make sure that the sections are going to fail in a specific way. We always want the steel to fail first, or steel to reach its yield strain first before concrete reaches its compressive strain at failure, which is we have taken it as 0.0035. Okay. So as we have seen in the previous material module also, you may remember that when concrete fails in compression, it's a complete destructive failure. Okay, so the material undergoes complete disintegration. So we have to be careful. We don't want concrete to reach its failure strain before the steel reaches. Finally, anyway, the final failure will be, if I'm testing some beams in flexure, the final failure will be by concrete failing in compression. But before it reaches that failure strain, we want to make sure that the steel is going to yield first, and it is going to give you a lot of stretching and warning before concrete reaches. So this is the failure mode that usually we design for. So that's also called as an under reinforced failure mode, which we will talk about it in the coming slides. Right. So these are the assumptions that we are making while we do the flexural analysis. Now, let's see. I kept talking about moment curvature analysis. Why is that we need to do moment curvature analysis? So it gives us an idea if for if I want to compare the performance of, let's say, a particular beam with the different amounts of steel, or if I want to change the strength of the concrete, I want to compare between two things: how much strength is increasing, how much uh, rotation capacity that particular section is. For that, in a normalized way, if you do moment curvature analysis, we can get a very good idea how that particular cross section is behaving with a certain reinforcement and concrete strength what we have assumed. So to compare the different sections, it is easy for us to compare so that we can compare apples to apples. So that is the reason we do moment curvature analysis. Uh, so let us see now for that how the strain and curvature is related first. Then we will see how the moment and curvature is related first. So in this example, what we are taking is a simple, simply supported beam, okay, and which is subjected to 2-point loads that we have seen here, okay. So this is these are the 2-point loads. So if I take the small elemental length, which is dx, okay, and I'm also saying that my reference axis is this, okay, which is x. So I'm taking this small elemental length dx at a distance of x from the left support, which is my origin. And I can also tell that this deflection, we are going to write this deflection as, let's say, as v, okay. So if I write this deflection as v and my reference x-axis at the left support, which is at a, and then I'm taking a section x dx, a small elemental length dx at a distance of x from the origin. Then if I look at this, if I blow up this section, and it's a rectangular section, let's say, and a small elemental length if I take it. So what we can see here, this before deformation, of course, at the neutral axis. So this is going to be neutral axis. The elemental length is going to be dx. Then any fiber that I'm taking at a distance from the neutral axis, let's say the distance is y. Okay, so we have taken this as y. So that distance is also, let's say that is ds. Okay, so before deformation, of course, dx is equal to ds because both of them are not undergone any deformation. So the length of this element dx will be equal to that of the length of the element ds because the member has not undergone any deformation. So now the same thing, if you start up increasing this load P from 0 to certain value, let's say 30 kilonewton or 40 kilonewton, now the beam is bent. So as we've seen in the previous things, the vertical lines will remain vertical and it is going to rotate. However, if you look at the horizontal lines, depending upon whether that line is above the neutral axis or below the neutral axis, it could be in compression or it could be in tension. So if you see here, if I consider this as my neutral axis and if I take this as y, right, so you can see here the horizontal lines above the neutral axis is going to be in compression, below the neutral axis it is going to be in tension, right. So and also you can see that if my y is larger from the neutral axis, the compressive deformation or tensile deformation, if I'm taking compressive deformation at the top, it is going to be higher. Similarly, if it is at the bottom, again the elongation is going to be higher. Or in other words, the distance of the fiber from the neutral axis tells you also how much strain that particular element is undergoing. Okay, so now when you do this as a simple circular bending, if you do take it and if I connect these two lines, so it is going to go and join here, then we call this thing as radius of curvature, where your element is going to bend like this, okay, which is this, right, and is going to bend like this. So this we call that as r, which is your radius of your curvature, right. So now what we can do is we can also express in terms of strain. So now you can see here the ds, what we have seen here, it has become ds prime, and dx is your elemental length at the neutral axis. At the neutral axis we know that there is not going to be any change in length, so dx will remain as it is before deformation and after deformation. Now if I want to calculate what is the strain in the fiber at a distance y from the neutral axis, ds has become ds prime. So the strain is going to be change in length by original length. So we can write that as ds prime minus ds divided by ds, because this is your change in length, right? This is your change in length, okay? And this is your original length. So this is the way we write for your strain. And also we can write from your circular bending. So if the elemental length has undergone some change in rotation, which is d theta, and we know that the dx can be written as, because here the dx is written into r. Okay, so if I erase this, okay. So here the R is actually measured from here to the neutral axis only. Okay, so this is your R. R is measured up to neutral axis. Okay, so you can see that now what would be ds, and ds we know that it is equal to dx, because the original length before deformation ds is equal to dx. Now what is dx? Dx can be written as r into d theta. Okay, so this dx, if you look at it, it can be written as r into d theta from your circular bending, right? So it is bent into the circular arc. So that deformation can be written as r into d theta. Now what is ds prime? Similarly, if you look at it, what is ds prime? So from here to here, what is the distance? Which is nothing but r minus y. Because this is the distance we have taken. Okay, this is the distance which is y. From the neutral axis, I am taking the fiber at a distance of y. So the ds prime from this location, it is going to be r minus y. So what would be the length for ds prime? Ds prime can be written as r minus y into d theta, right? So again for this, the change in length, now if you substitute for ds and ds prime into the strain equations, you will find that the strain is nothing but r minus y into d theta minus r d theta divided by original length, which is r d theta. So why is it we are doing this exercise? We want to relate, first of all, the radius of curvature to strain and the distance of the fiber that I am looking at. So if you simplify this process, for example, r d theta will get cancelled. So and you will say that epsilon is nothing but equal to, so epsilon is nothing but equal to, so if you simplify that, epsilon is nothing but basically minus y d theta by r into d theta. So d theta will get cancelled. So and also you can write that as 1 by r is nothing but epsilon by y. So this is your radius of curvature. R is radius of curvature. What is 1 by radius of curvature? It is nothing but your curvature, which is nothing but your rotation. How much the section has actually rotated. So which we always also written as phi, which is equal to your 1 by r. Again, the curvature is nothing but epsilon by, so it's nothing but your epsilon by y. Epsilon by y. So if I fix a particular curvature, so you can see here that, okay, so the curvature is nothing but strain divided by the distance of that particular fiber from the neutral axis. So this is a relationship between strain and curvature. So now we can see here for a particular curvature, we can see that if I'm taking the distance, if I take the higher the distance, okay, for a particular rotation, then you can see that if I keep this as a curvature, if I keep it as a constant, you can see that the strain is nothing but curvature multiplied by the distance of the fiber from the neutral axis. Okay, so you know that. So now we have taken this relationship between curvature and strain. Okay, now let us see what is the relationship between. Okay, our objective is to see how the moment and curvature is related. Now, what we have done is we have developed a relationship between curvature and strain. Okay, so we can see curvature is nothing but strain divided by the distance of the fiber at which I'm calculating that strain. So, or in other words, phi or phi, which is nothing but equal to epsilon by y. Phi is your curvature. Phi is also, it is equal to 1 by r, where r is your radius of your curvature. Okay. Now we have established the relationship. Now let us see how the curvature and moment are related. So for that, we will again go through a simple elastic beam theory. I am taking a small cross section with the Cartesian coordinate systems x, y, and z like this. Okay. So for this, if you look at the internal forces. Of course, this particular section can be subjected to horizontal force, which can be compression or tension, or it can be subjected to shear, which is V, or it can be also subjected to bending moment. Now, let's say that if I take a small elemental length, okay, which is We have taken that as dy. Okay. So, and we know that from Cartesian coordinate systems. So if I'm looking at this stress sigma xs, how is it being noted? So the first, in stress notations, the x indicates in the plane in which it is acting. Okay. So the first one, sigma x, the first indicates it, the plane at which it is acting. So, for example, what is an x plane? X plane is a section that is perpendicular to the x axis, the chosen reference axis. Similarly, what is z plane? Z plane is the section that is perpendicular, or the plane that is perpendicular to the z axis is called as z. In this case, we are dealing with x plane, which is perpendicular to the x axis. So, the first in sigma xx, the x indicates the plane in which where the stress is acting, and the second one it indicates what is the direction of the stress. So that is why if you look at this particular normal stress, sigma xx indicates that this stress is acting in the x plane in the direction of your x, which is basically along this, the force, the normal force m, f, right? So if I want to find out what is this force that is acting, what we have to do, force is nothing but stress multiplied by the entire area. So I have to sum this area sigma xx, which is acting over the entire cross section, right? So what would be, if I take this elemental length as dy, what would be the elemental area? Elemental area dA can be written as B times dy. Okay, so the stress multiplied by this elemental area will give me the force, but that is giving me force only in this small highlighted area. I want to calculate what is the total summation of the area that is acting over the entire cross section. For that, what is that we do? If I take the reference axis of the neutral axis, I have a section, you can see here, it goes, let's say if this is my neutral axis, the section goes up to h by 2 at the top and h by 2 at the bottom. Okay, so that is why we are integrating from minus h by 2 to plus h by 2 sigma xx multiplied by b into dy, which is nothing but your elemental area. So if I integrate that, I get my normal force that is acting on this section. Similarly, shear also we can write. Again, shear, what is it we do? We are looking at it, the stress that is acting on the x plane, but now we are looking at what is the stress in the y direction. So that is why you have sigma xy. Again the same, so sigma xy multiplied by b into dy, when I integrate it from minus h by 2 to h by 2, then I get my shear, which is v. Now what is bending moment? Bending moment is, it is not only about the force, the horizontal force that what it is acting. If I have to take the moment of that force about the neutral axis. Now what is then you are looking at the this small element is actually dy. If you say that, it is actually taken at a distance of y from the neutral axis, like what we have seen here. Okay, so if you see here, we have taken at a distance of y. So for example, this is the location, it was at the distance of y from the neutral axis. So same way here also, what we are calculating is basically the force multiply the moment of this force about the neutral axis. That is why here you have y is also that is coming. Okay, so that force, if I'm taking moment about the neutral axis, I get this sigma xx by times dy is nothing but your my moment. Now we can also do a little bit of simplifications. When you integrate this, we know that b dy is nothing but your elemental area. Now, for example, sigma xx, for if the material is going to be remaining elastic, then we know that stress and strain can be expressed in terms of linear elastic behavior, as stress is nothing but elastic modulus multiplied by the strain. Now, what are the expression for strain that we have derived from the previous expression? So, epsilon, we have taken that as basically curvature, right, multiplied by y. Right. Now again, what is phi? For phi, we written that as 1 by r. 1 by r is the inverse of your radius of curvature is nothing but your curvature. Now the strain is curvature multiplied by the distance of the fiber that you are taking. Right. So if I replace epsilon xx in terms of your curvature, so then it will become basically epsilon is nothing but y by r. Okay, because phi is basically 1 by r. So if you substitute here, then epsilon is nothing but y by r. So sigma can be expressed as elastic modulus multiplied by the y by r for that particular distance. Of course, I have to integrate with this. So now sigma is also I'm expressing in terms of your elastic modulus and the distance of the fiber. Now when you integrate, if you substitute back into this, so then what happens? Sigma xx become E multiplied by y by r multiplied by again by dy. Okay, so E is anyway material constant. I can also, for a particular rotation, 1 by r can be taken out. So if you do that, then what happens? Basically, this becomes m is nothing but e by r multiplied by integration minus h by 2 plus h by 2. Then what do that we have? D y square dy. Okay. Now, what is this b into dy? B into dy is nothing but your elemental area. From your strength of materials, we know that. Okay. So this in other words, it becomes minus h by 2 to h by 2 becomes d dy is dA. So it's going to be y square dA. Okay, which is nothing but your moment is nothing but your E by R times integration from minus h by 2 to plus h by 2 y square dA. From your strength of materials, we know that this is integration of your y square dA is nothing but your sectional property, that is nothing but your moment of inertia. So from this again we can relate this as m. Now I can, what I can do, I can put this y square dA as nothing but your moment of inertia. Then m by ei can be expressed as 1 by r which is nothing but your curvature. Okay, so this is a relationship between moment and curvature. Now you can see that this ei will remain constant for elastic material. Okay, when the system is not cracked, this is going to remain elastic or it is going to remain constant. Okay, e and I is not going to change for elastic material. But in reinforced concrete, concrete is going to crack and steel is also there. So this EI value will keep changing after the concrete cracks. Okay. So though your strain distribution will always be linear, but this depending upon the curvature at which the section is there or the how much the section is rotated, your EI value is not going to remain constant. So the EI is going to keep changing. Okay, so this factor we have to keep in mind. In fact, that is what we do in your serviceability deflection calculations. Depending upon the amount of moment that particular section is subjected to, EI value, some approximation is given, and the code gives you some formulations to calculate the reduced EI value. EI is also called as flexural rigidity. So we have to take a reduced value of flexural rigidity depending upon how much moment that particular section is subjected to, and whether it is close to ultimate strength or close to cracking strength, your EI value will change. So EI value will keep reducing as the section is subjected to more and more bending moment, moment close to that of your uh, ultimate capacity. Right. So in this section, as we have seen, so this is what we have taken. Now, what is it? Dx is equal to r into d theta. So as I said, EA is actually referred to as flexural rigidity. Again, EA will remain constant only for system that is in elastic stage. Okay, or when your strain levels are very low, then only if the section is uncracked, then EA can be taken as constant. That's what we do in your structural analysis or strength of materials. You take a constant value and calculate your deflections. But however, when we do moment curvature analysis, EA is not going to be constant depending upon what strain level that we are using for doing the calculations. EA will keep reducing. Okay, right. Now again we have seen that. So if I go back to this, dx is again r into d theta. So d theta is nothing but, now what is r? We have established the relationship. 1 by r is nothing but m by E, right? So you substitute for 1 by r like this. So it becomes d theta, or change in rotation is nothing but m by a multiplied by dx. Okay. So this is nothing but your curvature. Okay. So if I need change in rotation, what is that I have to do? I have to basically multiply the curvature by the elemental length, or in other words, I have to integrate the curvature for a small elemental length dx. Okay. So now, if deflection is in this case, let's say this is your deflection v. Okay. If you choose your axis deflection axis v as your positive upper, and then the curvature can be expressed in terms of x and v. X is nothing but the section at which we are taking the small elemental length dx. Okay, and we can determine the elastic curve. In most of the calculus books, it is shown that this curvature is nothing but d square v by dx square, where v is your deflection and it is taken as positive upward, and divided by 1 plus dv by dx square to the power of 3 by 2. So this is from your the relationship between curvature, and it is also including this higher order terms. So now we can see this is your 1 by r is nothing but your m by a. So m by a can be expressed in terms of this. Then and we have seen that the change in slope, or the slope of the elastic curve for the most of the structures, is very small. So you have seen that allowable deflections, if you look at your IS code also, even for service levels, okay, it is either L by 350 or L by 250, depending upon whether you are doing short term or long term deflections. So deflection levels at which we are dealing is going to be very, very small. Okay. So if deflections are going to be small, the change in slope dv by dx is also going to be nearly, you can assume or approximated to be equal to 0. So if I put dv by dx is equal to 0 here, then you can simplify this relationship between curvature and deflection like this. So m by a will become d square v by dx square. Okay. So this is the relationship between your curvature and deflection. Okay. Um, right. So this is the way. So d square v by dx square is equal to your m by a. Okay. So as we've seen, if somehow I can find this m by I, then I can also calculate or the distribution of your curvature along the length of the beam. By doing again integration, I can also find out what is the change in slope between the two segments, and also the deflection between the 2 points. Okay, that is what you should have studied in your structural analysis moment area theorem. When you integrate your curvature, when you double integrate your curvature, you get your deflection. Or when you integrate your curvature between one section to another section, you get the change in slope between these two sections. Right. So this is the relationship. So first we establish the relationship between strain and curvature, and now we have established the relationship between moment and curvature. Okay.